Before we finish our section on the strategy how to perform coupled CFD-DEM simulations, I would like to highlight two situations in which such simulations do not make sense. These are the CFD-DEM no-goes. First, these are situations in which an infeasibly large amount of particles would be in the simulation. Specifically, this is the case if we have small particles and large devices, e.g. a full-scale production facility with length scales of several meters. One should use an Eulerian description in such situations. Note that there are a few Lagrangian-based concepts, e.g. coarse graining, available for such applications, but these are more exceptions than the standard, since they, currently, often lack reliability and robustness. The figure here at the bottom should illustrate the huge increase of the particle count when going from level A, i.e. a particle resolved description as illustrated and discussed before, over level B, an unresolved CFD-DEM simulation of clustering phenomena, for example, to a full-scale description of a gas particle system for which we clearly prefer continuum-based models. Examples of what are CFD-DEM no-goes include large CFD simulations of fluidized beds, as shown here in the figure, the fluidization of small particles, for example nanoparticles, or the simulation of dusting phenomena. The second set of situations in which CFD-DEM coupling does not make sense consists of situations in which there is simply no need to use the DM. For example, if particles do not or only slowly move, the DM may not be necessary at all. In such situations, it is often sufficient to use a porous zone approach. An example is shown here at the bottom that illustrates the concentration distribution in a catalytic fixed bed reactor. The flow here is from the top to the bottom, and in which individual particles are resolved with a classical CFD mesh. Another example would be a leaching process in which particles may be partially dissolved by an ambient liquid and shrink only very slowly. Another situation for which coupling is not meaningful includes high Stokes number applications. Here the CFD part can be safely neglected simply because the particles have too much inertia to see the ambient fluid flow. Along the same way of thought, very small Stokes numbers do not motivate CFD-DEM coupling. Especially in case the flow is dilute and the particles are small, a relatively simple CFD-only simulation will be sufficient. Last, in case the flow is described by simple physics, e.g. moderately dense flows of spherical particles, continuum models, such as the two-fluid model, may be favorable compared to a CFD-DEM simulation. This is mainly due to the lower computational cost for a similar level of precision in the results when using a continuum model. Examples that underline this set of no-goes include the already mentioned fixed bed reactors, as well as fast granular flows in high shear mixers or granulators. That was it already for this part of our unit on CFD-DEM coupling. I hope you liked it. We now dive into some relevant details of computational fluid dynamics in a chapter that I have called CFD in a nutshell. With this chapter, my goal is to summarize all relevant details that are needed in typical CFD-DEM and multiphysics applications. So it should contain a lot and perhaps more than you need. However, I spared out chemical reactions in the model equations as this is a topic of its own. Also, topics I would call complex particle physics have been spared out. The latter may include turbocharging, for example, and we have no time to even scratch on the surface of these highly complex topics. Let us start with the fluids governing equation straight away. First, we have to consider the mass balance equation, which for a fluid in a multi-phase mixture reads as follows. The accumulation plus the outflow of mass, often called convection, at each point in space must equal 0. Note that a positive divergence of a vector field means it acts like a source, meaning there is outflow of the considered vector field. As you see, we have kept the fluid density ρf inside the derivatives, meaning that this equation can also be applied to compressible fluid flows in which the fluid density depends on pressure and temperature, for example. Please note, however, that this equation neglects any mass transfer from the fluid to the particles or vice versa. Next, we need to consider the momentum balance, often also referred to as the Navier-Stokes equation, which for a fluid in a multi-phase system reads as follows. The accumulation of fluid momentum, i.e. the acceleration of the fluid multiplied with the local density, and the outflow of momentum equals the sum of 4 contributions. The first one is the contribution of the pressure gradient here in the gray box. Often the pressure gradient is decomposed into a dynamic fluid pressure gradient P dyn, and the product of a mixture density and gravity. This essentially removes a hydrostatic pressure gradient, which is sometimes convenient. The second term is the fluid deviatoric stress term here in the blue shaded box. Note that this term is often of low importance compared to the other contributions, especially in flows with a high particle to fluid density ratio, such as in the case of gas particle flows. Thus, you will often see a laminar fluid stress model, and this should not surprise you. It simply means that using a more detailed turbulence model would not be worth the additional computational effort. The next term is very important and hence placed inside a red shaded box. It is the interface interaction term. Since you should already understand the main reason why we do coupled CFD-DEM simulations, you should already know that this term quantifies the transfer rate of momentum from the particle to the fluid phase. Most important is the fact that in situations that are characterized by relatively dense granular flows, this interface interaction term can dominate the whole equation and balances, to a large extent, the pressure gradient term. It is hence often important to make good predictions about the interaction forces, and the flow solver should then calculate a correct pressure field. Last, we have the gravitational term. Please note it contains the fluid density and hence in gas particle systems might be small compared to all the other terms. That is it already for pure flow, and we transition to the next topic, which are the governing equations for multiphysics applications. What you will see below is a general transport equation for the fluid in a multiphase mixture. As you can see, the scalar quantity, e.g. the thermal energy of the fluid, a mole fraction or a dust loading, is denoted here as theta. Same as for the momentum, on the left hand side we have the accumulation term and the convective transport term that quantifies the local outflow at each point in our computational domain. The right-hand side is relatively simple. First, we have the divergence of a diffusion or dispersion flux. This flux is characterized with dF, referring to an effective diffusion coefficient. As you can see, this term is proportional to the gradient of the scalar quantity we want to track. The second term is the interface interaction term, which in analogy to momentum balance can dominate the right-hand side. We do not have time to go into details, but same as for the drag force, which we will discuss in detail soon, we need to use correlations to calculate the transfer rate of scalar quantities that account for the local Reynolds number and the local particle volume fraction. For example, for heat transfer, this is the famous gun correlation, for which you see the reference here below. We note in passing that the above general transport equation is applicable to almost everything. For example, vapor, heat, molar species, even small droplets and dust, as long as the material follows the fluid trajectories. Even in the case the material has a slip relative to the fluid, this can be repaired, e.g. by introducing a local drift velocity. What I have to admit is that there are certain physics that cannot be captured by this equation. This is radiative energy transfer. You will see details later, and things like electrostatics need special attention. Anyhow, as you now are aware of this, let us move on to look at some results that are obtained when applying this set of equations to real-world problems. First, this is combined heat, vapor, and droplet transport in an industrial process. Such processes include, for example, the coating of tablets in rotating pans, fluidized bed granulation used in food and pharma applications, or so-called fluid coking, which is used in petrochemical applications to crack large hydrocarbon molecules. The complexity of phenomena occurring in such industrial processes is illustrated in this figure from Asghari-Shari et al. Let's start with the liquid droplets here on the left. They may collide with particles and deposit, and consequently may be dispersed by the particle motion. The liquid may also be soaked up in the pores of the particles, resulting in intraparticle transport phenomena. As you know, liquid may also evaporate, forming vapor, which is illustrated here at the bottom right of this figure. Of course, also droplets might evaporate while suspended in the gas, adding additional complexity. All this is affected by the local temperature, which is impacted by heat exchange from and to the particles. You see, once we start considering multiphysics, a whole range of topics pop up. Since we have not enough time to go into the details, I simply want to refer here to the publication of Asghari-Shari et al. That documented one of the first full physics models of such processes in 2016. An overview of multiphysics phenomena in a specific application, namely fluidized bed granulation, is provided on this slide, which I have taken from the recent work of Asghari-Shari et al. In the year 2023. The figure highlights the position of 4 different modeling approaches in a length and time scale diagram. Specifically, on the smallest and shortest scales, we have pore scale models. They are useful for predicting intra-particle phenomena, e.g. vapor transport and liquid transport inside the pores of the particles. Microscale models contain classical CFD and resolved CFD-DEM models, e.g. to study the formation of liquid bridges between wet particles as shown here, or the associated forces. When talking about mesoscale models, we often mean unresolved CFD-DEM simulation models. As shown here, they can be used to predict the local moisture content, here denoted as LOD for loss on drying, or the local temperature for a subsequent identification of well-mixed zones. The macroscale models are of great industrial importance since they aim at the prediction of the performance, e.g. of the drying rate in an industrial process. However, they do not involve fluid or particle flow simulations, since they must be very fast, e.g. to be able to evaluate them during the actual operation of a process. Such an on-the-fly process simulation is needed since macroscale models are sometimes used in the control of a process.